All right, guys. So today we are now in AP Test Prep Level 2A. Okay, we're on to level 2. We made it. We are now in the underground. Okay, so the AP test wants us to start covering, or wanted to cover, going from the periodic trends of electronegativity. I definitely spelled that wrong. Electronegativity. There we go. Electronegativity. So reminder, that is the atoms, not ability, but I keep wanting to say desire. The atoms, for lack of a better word, the atoms, quote unquote, desire to hold electrons. Okay, reminder that atoms do not have minds of their own. They cannot desire things. They are more stable when they have more electrons. Maybe that's a better way to say it, but whatever. So the atoms desire to hold electrons. Now, from the electronegativity, the trend on the periodic table is as we went up and to the right, we had increase in electronegativity. Okay. Now, some important things to understand is that hydrogen is like right between, I believe, boron and carbon in terms of electronegativity. Okay. Hydrogen is right there between boron and carbon. Now, the difference in electronegativity, determines the type of bond. Okay, so the difference in electronegativity determines the type of bond that is going to form between, we'll add that, two elements. Okay, so let's take, for instance, hydrogen and hydrogen, okay, otherwise known as H2. Okay, we can look at that now and say automatically, yes, covalent bond, it's between two nonmetals, and they're going to be sharing their one electron. Good. Now, the electronegativity is what determines that, okay? There is no difference in electronegativity between H and H. They have the same electronegativity. So the difference is a number of 0. This number determines that 1 is going to be covalent, and 2, that it is going to be a non-polar covalent bond. Okay, so not only are they going to be sharing those electrons equally, they are also going to be sharing them equally. Okay, that's important. Okay, now let's look at, say, sodium and chloride. Okay, So we are forming table salt, sodium chloride, and the difference in their electronegativities is so high, it is above 1.7, and that means that it is an ionic bond. Okay, so the electronegativity of chlorine is so much higher than the electronegativity of sodium that it's not going to be a shared bond. It's going to be chlorine is taking an electron from sodium, and it's holding onto that electron wholly. And then these bonds, or these elements, are bound not by a sharing of electrons, but by a positive and a negative interaction. Okay? These cutoff numbers are important to know. You may be given a table of electronegativities for elements and determine, which ones are polar, nonpolar, and ionic. Okay. Now this next one, let's say we have H and F. Okay, so we have hydrofluoric acid, HF. Its difference in electronegativity is greater than 0.5. Okay, some people say 0.4, other people say 0.5. It is very close in number, but it is greater than 0.5 and less than 1.7. Okay, so their difference in electronegativity is greater than 0.5, less than 1.7, and so this means that they form in a polar covalent bond. Now, Mr. Fry, what does it mean to be polar? Okay, quick review. Let's go ahead and circle that. Quick review. Polarity means an unequal sharing of bonded electrons. Or not only bonded electrons, but an unequal distribution of negative charge. Okay, so if we look at the Lewis structure here for hydrofluoric acid, and if we also look at the trend for electronegativity, fluorine is the most electronegative atom on the periodic table. So it wants to hoard those electrons. Okay, it wants those electrons. Lack of better words, it is more stable with electrons. Okay, hydrogen, not so much. Okay, compared to fluorine, not so much. It doesn't really need those electrons as much as fluorine. It doesn't need stability in electrons as much as fluorine does. So not only that, so the bond is going to be polar. The electrons are going to be hoarded more towards the fluorine than the hydrogen, and so we have a partial negative on the right side with the fluorine and a partial positive on the left side with the hydrogen. Now, not only that, fluorine also has these unbonded, these lone pairs of electrons. That means there's a buildup of negative charge on the right side here. And so that means that it also is going to contribute to the polarity of this molecule. Okay? That's the polarity of molecules and bonds. Right now, when we're talking about differences in electronegativity, that is just the polarity of the bond itself. Okay? So if we say, for instance, look at carbon tetrachloride. Okay? So chlorine has a higher electronegativity than carbon does, and so it does have polar bonds. Okay? However, this is not a polar molecule. Because the charges are equally distributed on the outside of the molecule. The bonds are polar. Okay, there is an unequal sharing of negative charge in the bonds. However, the entire outside of this molecule is negative. Okay? So there's not one side of this molecule that is positive and one side of it that is negative. The entire outside of that molecule is negative. Okay? So it is a non-polar molecule. Okay, there's not a difference in polarity or difference in charge on the molecule itself. Okay, so this electronegativity only goes for the single bond. Okay, the difference in electronegativity tells you if the bond itself is polar, nonpolar, or ionic. Okay. Now the last combo that we have is a metal and a metal. So metal and a metal is different. Let's go with copper. So we have copper and copper. Okay. Copper and copper, neither one really need the electrons. And so neither one of them need the electrons to be stable. Okay. So what ends up happening, let me spread those out. Do larger ones more spread out. This is all copper. This is like a sheet of copper. Okay. What ends up happening is that those electrons that the others would like to have, like a full valence shell, all of that jazz, but they don't really need their excess. So those valence electrons are a free electron movement throughout the entirety of the solid. Okay. This is called delocalization. Okay. And these electrons that are swimming about are not associated with any specific atom, and is the reason why metals can conduct electricity. Okay, they have free electrons that can move from atom to atom, and if you put a positive charge at one end of that metal, then those electrons are going to be attracted to it, and so they're going to move towards that positive charge. Okay, that's why these things can conduct electricity. All right, so that is AP Chem test prep level 2A. Okay, we are now into atom bonding, atom interactions, and all of that jazz. Okay, so reminder, if you have any questions, let me know, and good luck studying and staying healthy out there, gang.